Greeting. Welcome to the lecture of Introduction to Power Engineering. Today's lecture gives an introduction for the technology of converter and its system aspects, as well as the transmission line technology. The discussion will be focused on the technology of point-to-point connection of HVDC system. High voltage direct current HVDC system has been used in power transmission system for over 50 years. Its main applications are the interconnection of non-synchronous network, long-distance transport of electrical energy, and submarine and underground cable transmission. There are two main systems of HVDC. The most commonly used systems are based upon current source converter, which is abbreviated as CSC, or line commuted converter LCC HVDC, using thyristor type valves. Secondly, voltage source converter, which is abbreviated as VSC HVDC technology, which uses fast power electronic switches such as MOSFET and IGBTs, is a recent development which is seen as a game changer and as the key enabling technology for future DC grid. Line commutated converter HVDC or classic HVDC is built using thyristors in a current source converter topology. Thyristors can be switched on but need the current to pass through zero in order to switch off. The angle at which the thyristors are switched in is called the firing angle. The bottom right diagram shows the basic circuit of a HVDC connection over here. It has the component of an AC transformer connected to a 6-pulse thyristor bridge. The typical waveform of such a device is shown in the bottom left diagram. In LCC system, the commutation process is caused by the system inductance and causes a short overlap period during the transfer of the current between two branches of the converter where both branches conduct. The commutation period is expressed as the commutation angle mu naught. In order to reduce harmonics in the AC system, additional harmonic filters are needed. A reduction of harmonics can also be obtained by utilizing converters with a higher order of pulses, such as up to 12, 18, or even 24 pulse converters. Most classic HVDC configurations use 12 pulses converters as shown in this diagram. These 12 pulse converters cancel out the 5th, 7th, and 17th and 19th harmonics. The transformer of a 12 pulse bridge has a YY delta 3 winding configuration, such as shown over here, or a combination of YY and Y delta transformer formulated with a single phase transformer. The transformer here can be used either a 3-phase transformer or a single phase transformer. The leakage reactance of the transformer is typically between 10 to 18% in order to limit the current during a short circuit fault of the bridge arm. The bridge arm is considered this single legs. In order to reach the required higher voltage, several thrusters are placed in series. A single thruster can block up to 8.5 kilovolts and carry current up to 5 kiloamps. There is normally redundancy built in so that a single thruster failure does not lead to a failure of the entire HVDC link. The current through the classic HVDC system is always in the same direction. Reversing the power flow is done by changing the polarity of the voltage. Several configurations are possible, such as monopole, bipole, both with or without ground return. A monopolar link has one conductor at a high DC voltage. The other conductors can use either the ground or C as the return path or a metallic return wire. The return metallic wire is used when harmonic interface and or corrosion are an issue. Since the corona effect is more important with positive than negative voltages, the monopolar link is normally operated with negative polarity in case of overhead line. The configuration of the monopole is shown in this diagram. Although systems with a single conductor and earth or C return are technically easy and economically beneficial solution, they cannot always be used because of the possible effects of corrosion on metallic pipes in the ground and the possible negative environmental effect on animals, especially fish and birds. However, several of these monopolar configurations are currently in operation. Amongst other, the recent Baltic cable, a connection between the German and Swedish power system, and the Greta connection that is between Italy and Greece. System with the metallic return wire have the advantages that the metallic return only has to be insulated for a very low voltages. This significantly reduces the need for insulation material around that wire and hence the cable cost is reduced. The base link, it is a connection between Australia and Tasmania which is in use since 2005, is also of the monopolar type with metallic return. Also, the connection between Sweden and Poland is of this type. The bipolar link is the most commonly used topology for modern LCC HVDC connection of high power rating. Each terminal has two converters of equal rating. Between the converters, the midpoint can be grounded on one or both sides. In case both sides are grounded, there is virtually no current flowing through the ground during normal operation, since the two converters are operated symmetrically. The diagram of the bipolar configuration is shown over here. Bipolar system requires lower voltage rating for equal power transfer compared to monopolar system. The monopolar connection requires a pole of double voltage rating while the bipolar system would require two cables of single voltage rating. A second advantages come from the ability to use the 50% of the system during maintenance fault of one module cable of a bipolar link by using the ground or a metallic return as a return path. For this reason, bipolar system can be equipped with the metallic return as well. An example of a bipolar connection without metallic return is the node net link between Norway and Netherlands. Another configuration of HVDC system is called back-to-back. In a back-to-back connection, the two converters are located in close proximity of each other. The typical application is the separation of two independent power systems. These systems are not synchronized or on a different nominal frequency. The DC voltage in the intermediate circuit can be selected freely at HVDC back-to-back station because of the short conductor length. Because of the short distance, the line resistance is low and the DC voltage can be kept relatively low, resulting in a smaller valve hole. When neglecting the commutation, the required active and reactive power at the terminals of an LCC HVDC station can be approximated as written in these equations. Here, P and Q is the active power of the converter, UAC is the RMS AC voltage, IDC is the DC current, where the firing angle alpha of a rectifier should be replaced with the extinction angle gamma at the inverter side. So if we have to apply this equation for the rectifier, we call this as a alpha, but if we have the inverter operation, then this alpha is replaced by the extinction angle and the whole equation is valid. When no reactive power compensation is used, the reactive power absorbed at the terminal is 0.5 to 0.6 per unit at rated active power. This has serious consequences for the control of voltage at the end terminals. The higher current and losses in the AC grid will be appear and the voltage stability of the system will be affected. Therefore, it is often stated that LCC HVDC link can only be inserted when the short circuit ratio, which is abbreviated as SCR, is high enough. The short circuit ratio is defined as the ratio of the short circuit strength of AC system to the DC converter megawatt rating. The strength of a AC system can be calculated as the square of RMS AC voltage divided by the Thevenin impedance of the network. SCR can also be referred as effective SCR, ESCR, whose calculation includes the effects of the application related to the DC link, such as transformer, shunt capacitor, filter, and so on. The effective SCR is defined as the ratio of short circuit strength of a AC system minus the reactive power compensation to the DC converter megawatt rating. The SCR and ESCR can be classified as high, moderate, low, and very low. The system is considered to be strong when the SCR is equal or greater than 5 or effective SCR is equal or greater than 4.5. The system has moderate strength when the SCR is greater than 3 but lower than 5, or effective SCR is greater than 3 and lower than 4.5. Further, a system is considered weak when SCR is greater than 2 but equal and lower than 3, or effective SCR is greater than 1.5 or equal or lower than 2.5. A very weak system would be when SCR is lower than 2 and ESCR is lesser than 1.5. The control of HVDC link has an important impact on its interaction with the AC system. At low and very low SCR, the connection of LCC HVDC link becomes difficult and requires specific tuning or might require additional installation such as SATCOM. However, specific studies have to be performed in order to assess the full impact. Furthermore, the HVDC link itself does not contribute significantly to the short circuit power of the AC power system. Since the AC system has to deliver a significant amount of reactive power, this will have consequences when the system itself is weak. The following problems can arise. The dynamic overvoltages in the case of DC transfer interrupt, voltage stability issue especially at the inverter side, harmonic resonance as the voltage distortion is higher, and voltage flicker. The traditional solution to cope with the high reactive power demands at the end terminals of an HVDC link are an adjusted control of HVDC link installation of switch capacitor or dynamic reactive compensation such as SVC static var compensator or SETCOM static compensator, or when possible the extinction control of a nearby generator. Thyristor-based HVDC system has different converter topologies as shown in the diagram. The capacitor commutated converter is a configuration used by certain manufacturers in which a series capacitor is inserted between the transformer and the converter, which is shown in the bottom left diagram. Other manufacturers use a different configuration with a similar result, such as shown in the bottom right diagram. This solution is called a control series capacitor converter and uses a thyristor control series capacitor placed between the power system and the AC transformer. These advanced configurations have the advantage that they can operate in a weaker AC grid and that they can also withstand voltage drops much better. Furthermore, the reactive power requirements are significantly lower. The main components that comprise the HVDC systems are the converter station, the transmission cable, and the earthing electrode. A schematic overview of an LCC HVDC station is given in the diagram. Identical converter stations are installed at both ends of the HVDC cable. The thyristor valves of converter have to be perform the following tasks, such as connecting AC and DC sides, conduct a high current up to 5 kiloamps, block a high voltage up to 8.5 kilovolts, control DC voltage via the firing angle, operate fault tolerated and robust. Since the DC voltage is higher than a maximum blocking voltage of a single thyristor, several thyristors are placed in series. Similarly, the current capability of a single thyristor can be increased with the connection of several thyristors in parallel, which, however, is normally not needed. Normally, the thyristors are installed in modules which are placed in a stack, making maintenance straightforward. The thyristors can be electrically triggered or by using light. Strictly speaking, transformers are not always needed in HVDC installation. However, they are practically always used so that they allow optimizing the DC system voltage independent of the AC transmission system. Tape changers can be used to manage the voltage, which can reduce the losses. Using rectifier with a high pulse number is possible. They also limit the short circuit current into the valves, working as a smoothing reactor. Depending on the application, different transformer and rectifier can be used to obtain a techno-economically optimum solution. Because of its size and the choice for a transformer often depends on the available transport means, the location of the substation and its space requirements or the construction site. The larger HVDC system mostly make use of multiple single-phase units, although the principle of LCC HVDC transformer are quite similar to those of traditional AC transformer. There are several practical aspects of HVDC which cause the transformers to be more complicated, such as oversaturation of the core through DC current, higher test voltages, and specific arrangement to connect the winding. An HVDC link requires several filters and reactive power compensation devices. If there are no nearby generators that can compensate for this reactive power, additional capacitors such as SETCOM has to be installed. Furthermore, switching thyristor causes high harmonic distortion on the power system voltage, possibly influencing nearby installation. These harmonics have to be mitigated by additional filter. The DC filter is formed by the DC smoothing reactor which flatten the DC current. Other components of HVDC system includes earthing electrodes, protection devices, surge arrestor, AC and DC switchyard, auxiliary equipments, cooling system, and control system. In this lecture, we have discussed about the basic components of line commutated converters based HVDC transmission system. In the next lecture, we will discuss the component of voltage source converter based HVDC transmission system. Today lectures end here. Thank you for listening.